Multivariable calculus, we're on lesson 15.8, and we're going to look at a new way to represent a point. In 3 dimensions, there is a coordinate system called cylindrical coordinates, and it's amazingly similar and close to polar coordinates, and it makes problems very convenient. So in cylindrical coordinates, a point P is represented by this ordered triple. It's not an x, y, z. Rather, it's an r, theta, and z. And just like last year in BC Calc, there are equations relating the rectangular and the polar, so you can naturally link that to rectangular and cylindrical. The polar is going to come right back. It's exactly what we saw last year. We know that if we were to have any point x, y, that we could go right x and go up y, and there'd be a distance r and an angle that's made theta with the x-axis. We know that x squared plus y squared equals r squared. That's coming from the Pythagorean theorem. From trig, right triangle trig, SOHCAHTOA, we easily could solve that x is equal to r cosine theta, y is equal to r sine theta, and likewise tangent, which is opposite over adjacent, tangent of theta is equal to y over x. The z, which is, you can consider it your height, it's going to be the same thing. So this is really, really nice in the sense that what you've done in the past with polars is exactly what you're going to continue to do. And whatever z value, whatever height you'd have, so to speak, you will just keep. So let's do a problem together. Convert this cylindrical, which is r, theta, and z, into rectangular coordinates. Well, we know that x is r cosine of theta, and y is equal to r sine of theta, and your z is actually one and the same. So, here we're going to say 2 times the cosine of 2 pi over 3. Y is going to be 2 times the sine of 2 pi over 3, and your z is just a 1. So what is the cosine of 2 pi over 3? Well, the cosine of pi over 3 is a half, but in this quadrant of 2 pi over 3, cosine is negative. So this is 2 times negative 1/2. Our x will be negative 1. The sine of 2 pi over 3 is going to be root 3 over 2. You can see the 2's cancel out, and you'll just have a radical 3. So what is your x, y, z, this ordered triple? Negative 1, radical 3, and a 1. And we are done. Likewise, we can take a look at an x, y, z and say, well, could we take this ordered triple and convert it into cylindrical coordinates? Well, you could definitely get your r value very quickly. You know that you'd have 3 squared plus negative 3 squared is equal to r squared, so that's 9 plus 9. We know that's 18, and we know as we take a square root, this is 9 times 2 in here, so this is going to be 3 radical 2. And to find theta, well, we saw up here tangent of theta is actually going to equal y over x, so that's going to quickly work out to negative 3 over 3. So we're saying tangent of theta would equal negative 1. But inverse tangent always went between negative pi over 2 and positive pi over 2. And we certainly would expect, if we were going in this fourth quadrant, to have a reference angle of pi over 4. We could say, well, negative pi over 4 because we're in that fourth quadrant. Our z was equal to negative 7. So as we would write an r theta z, we'd write 3 radical 2, negative pi over 4, and of course our z value is negative 7. So this is one way we could represent this point. Of course, you probably also remember from polars that you could also work with a negative angle, projecting it, or I should say with a negative r value, pardon me. If r is negative, we will work from the opposite quadrant. So you'd say, so what angle would this be if we're now in the second quadrant with a reference angle of pi over 4? You could say it's going to have to be 3 pi over 4. And this would be another way you could represent that. Remember, r being negative, just like we've seen with the polars, relates to projecting that point from the opposite quadrant. So let's go real quickly and think about how to do some calculus. Well, the calculus, you can see that we've got a little volume chunk here, a little slice of volume. And if we were to, say, take a look at what's happening in a little volume slice, you can see we'd have an r, and our theta would be moving just a tiny bit. This would be an arc length if we use the arc length formula, r times theta. So in yellow here, this would be r d theta. And how do you find the volume of a little box? Well, it's length times width times height. And that's very important for you to see that you'd have an r d theta times a dr times a dz. And of course, what you're going to notice is here we could very quickly change our integrand, and instead of just having an r dr d theta, we could have an r dz dr d theta. So that's the quick adjustment that you'd make with cylindrical coordinates. Now, cylindrical coordinates, of course, are going to be incredibly helpful for cylinders. And anytime that you might be relating into polar coordinates, it's very possible that these cylindrical coordinates might just help you out tremendously. So let's take a look at example 3. They're very kind enough to give us a picture, and they're telling us here's this solid. It lies within a cylinder. X squared plus y squared equals 1. That's a circle, of course, but with no specified z value. It would be a circle for any z value. So you could see that's your cylinder right here. And it says solid lies within this cylinder below z equals 4. Well, z equals 4 would be this top circle right up here. But above this paraboloid, wow, this paraboloid, z equals 1 minus x squared minus y squared, you can see they've put that little bit of a paraboloid. It almost looks like a little bit of a dome right here at the very bottom of your solid. And of course, we're going to have this solid where that dome is the very bottom of that solid. And this circle at the top, from the plane z equals 4, is the top. So we've got that solid, and we'd like to find the mass of it, but they're also going to have to give us density. The density at any point is proportional to the distance from the axis of the cylinder. So, when you read this, you're really getting rho. And you could very quickly say, well, my density function is going to be proportional, so that's some constant, multiplied to a distance from that point to the axis of a cylinder. So you can see I've drawn a point in space here. I didn't even specify its height, z, but what you can see more or less is you'd have an x distance and a y distance, an x and a y, and then you'd have this distance right here, that's d. You also get the very same thing at the very bottom of the xy plane. Now, what I'm pointing out to you, of course, as you're looking at this, you can quickly see then that what's going to happen is you get the Pythagorean theorem. You could say x squared plus y squared equals d squared, where d is the distance from the axis. The axis is the z-axis, that line going right down the middle of the cylinder. And that distance then is the square root of x squared plus y squared. So we'll have k radical x squared plus y squared. Well, they're asking us to work out right now what m is the mass, and we can do that. We're going to do that right now. The mass is going to be this triple integral over this solid, and here's your rho function. And of course, as we're looking at this, you can think, well, my goodness, it certainly seems very, very likely that we would like to somehow relate this into cylindrical coordinates. You don't have to. I want to be very clear about that. But my word, it makes life so much easier when you do. Here's what we're getting at. We know from our polar coordinates that x squared plus y squared would equal r squared. We know that x would be r cosine theta, y is equal to r sine theta. You get the idea. But in this solid, as we're looking at this, we could find any point, even this point that I drew in red right there. It could be represented as a certain distance from the origin, an angle theta, and a height. So here's the wonderful thing is we're going to work this out. We can very quickly do the following. We can say, hey, I'm going to have my triple integral right here. I'll have my k, but we know that x squared plus y squared is really r squared. And then dv is going to be an r, dz, dr, d theta. And I guess what I want to point out to you first is this. You know that you're going to begin looking at dz. And wow, as we're looking at dz, I just want to point something out to you. What are the boundaries of z? Well, real quickly, we could say that's the highest one, and down here, touching that little dome, that paraboloid, that's the lowest. Now, you would know that the biggest z value is going to be a 4. And the lowest z value is going to be this 1 minus x squared minus y squared. You can see that vertical line is really representing this. However, when we're going to go into cylindrical coordinates, it makes sense to convert your x's and y's into r's and thetas. I'm going to factor out that minus, and x squared plus y squared we know is r squared. So wonderfully and quickly, they already pointed that out to us. You can see we've got that right there. So that's kind of nice. And we can right now say the following. Our upper bound would be z equals 4. Our lower was the paraboloid 1 minus that x squared minus y squared, but we can convert that into 1 minus r squared. Now what? Well, you can very, very quickly find the following. You know that your r is going to, of course, always be from the origin down here, and if we were to just look just like we had before, with our work in the previous section, when we're looking at D, and I think in the past maybe we've made it green, whatever color we're going to make it, we can take a look at that circular base. I think that's a good thing to keep doing. You can see it's going to be a circle, and we already knew it would have to have a radius of 1 from that cylinder that we had. So we have x squared plus y squared equals 1. And, as we're looking at that, we're going to know, of course, and that's coming from right here, that our r is going to span from 0 to 1. And our theta will go between 0 and 2 pi. So that, hopefully, is setting the stage. As we just have this video finishing up,